So at the end of last lecture, we obtained the average spin or the average magnetization of a system, okay, near the critical point behaved as, so we explicitly have proportional to minus t to the power 1/2. Okay. I think this is the expression that we got. Explicitly, we have obtained that this average was plus minus square root of minus b divided by 2c. Where this b and c came from? So they came from the expansion, the expansion of the free energy, where we had 0 minus average m over h, okay, plus b m squared plus c m to the fourth. This was our assumption for the free energy as part of the Ginzburg-Landau theory. We obtained this solution, or more specifically that b, when t goes to tc, okay, is proportional to some constant. And here we had t minus tc, or tc minus t. T minus tc, yep, t minus tc. And specifically, t that we have over here was the reduced temperature, which is T minus Tc divided by Tc. This is the reduced temperature. Reduced temperature. Okay, so we have this exponent over here of 1/2. It looks like it's nothing really interesting, but it actually does. Because what happened in many systems that there is this order-disorder transition. So usually it looks like this. We already have this plot many times. Okay, so if this is the temperature or some external parameter, and the average m over here plays the role of the order parameter. So we know that for high enough temperatures, okay, for high enough temperatures, it was always 0 for high enough temperatures. It was non-zero for low enough temperatures. And there was a critical temperature that we termed Curie temperature, where a spontaneous symmetry breaking occurred. Okay, what we see that in the vicinity of this critical point, okay, the behavior is described, okay, it looks like a square root of the temperature, or the square root of the reduced temperature. What's going on over here is Tc minus t to the power 1/2. Why it's interesting? Because in many systems, very different systems, some of them magnetic, some of them absolutely non-magnetic, the behavior was near the critical temperature, described exactly by the same power law. Okay? Moreover, people started to measure this transition from order to disorder in different systems. Right? And what they have seen is that these exponents, you can find only a bunch of them. Okay? It's not that for a system of some thermal system is going to be 1/2, an absolutely different system is going to be 1/2.0 something. It was very specific values that this exponent actually obtained and being observed in nature. So if we plot the log of m, okay, if we plot the log of m as a function of log of what? Of t right, as a function of log of t, what we will see, okay, that because the exponent 1/2, okay, is transformed into the slope of a log, so we will see a straight line, okay, or at least a log of minus t, okay. We will see a straight line, and this is the behavior, okay, with a slope of 1/2. Okay. Now, for many, what is actually observed in nature, okay, if we plot this logarithm of m or some other order parameter as a function of minus the reduced temperature, we cannot see anything that we will like. We will usually observe only small numbers of possible lines, okay, 1, 2, 3, or 4. And what is mostly interesting is that different systems have exactly the same exponent or will follow exactly the same behavior in the vicinity of the critical temperature. This is why, okay, that those exponents got a name. They are termed critical exponents, and they define something that is called classes of system. Okay, so what we now understand that near criticality, different systems behave in a very universal fashion. And what exactly dictates their behavior? Some sort of a not very specific molecular interactions that are part of the system, but we now understand that this is something much more general, like a local topology, local dimension, or local geometry of the system, and not what are the types of the exact type of the forces that are there. And all of this is translated to the value of the critical temperature or critical exponent that we see near the critical point. So specifically for magnetization, the value 1/2 that we obtain from the mean field expression basically means that the system, it usually means that the interactions in those systems are always or almost always are short-ranged. Okay, so we need to have a high enough dimensionality and short-range interactions, and for such systems we will always see this exponent 1/2. Systems that their dimensionality is somewhat different, local geometry is somewhat different, will have different exponents. They are usually somewhere between 0 and 1, and there is not so many of them. Now, this got a lot of interest because it shows that there are universality near this phase transition point, near this critical point, and people started to first to see if there are other exponents, other critical exponents in nature that we can measure, okay, and then classify the different systems according to the behavior near the critical point. Okay, so what are other critical exponents that are there? Well, there are actually a huge number of them. Okay. The most interesting are, and that's the one that we are going to discuss, are the behavior when, so first of all, here what we see is the behavior near the critical point of the order parameter when there are no external field, okay? We can also ask how M behaves, okay, when for T equals Tc, but with external field present. Okay? So what happens, we have seen how this line behaves. Okay? Now we can say, let's stay at exactly the same critical temperature and start to increase, okay, and we'll start to increase the value of the external magnetic field. So for high temperatures, okay, it will look like this because there are small magnetic field that's present. That means that on average we will start to see some sort of a mean value for our magnetization, okay? And then it will go somewhat like this, okay? We can increase our temperature a little bit more. The mean value will rise a little bit more, and we will start to see something like this. Okay. Now we can measure the average magnetization, okay, as a function, okay, exactly at the critical temperature, as a function of growing external field. Okay. We can do this for many different systems. Okay. And what we observe that M, an average, is proportional to H to some power that is usually termed as 1 over delta. Okay? And again, exactly as for this 1/2 over here, okay? For this 1/2 over here, we can see only a few types of delta, okay, that can be actually observed in experiment. Okay? Let's first, now another exponent is what happens or how the average magnetization changes with external field for non-zero, for T smaller than Tc. Okay? So in the vicinity of the critical point, we can also ask what is the susceptibility, okay, this is the susceptibility, okay, the susceptibility of the system to external field. Why exactly those exponents? Because those are actually easily measurable quantities. We can apply external field, we can increase the external field, and we can measure magnetization. We can make the external field equals to 0, and we can make and we can measure magnetization, or okay, we can measure magnetization and we can actually measure the rate of change of the magnetization as we apply the external field for different temperatures. Okay. Over here, the exponent is termed gamma, I think. Right? Yep. So usually what people see that he is proportional to T to the power minus gamma. And again, those critical exponents, we see only a few of them. Different very different systems, the same critical exponent. Okay. Now let's try and compute for our mean field approach what is exactly this delta and what's exactly this gamma over here. Okay, so let's concentrate on delta, right, that we have over there, and ask the following question. So exactly, we can start with our free energy. Let's write it again. It's written over there. So F equals A minus mH plus B m squared plus C m to the fourth. Okay? Now, the next step that we did in order to compute this 1/2 behavior, okay, we took a derivative of F with respect to M, okay, and we solved for solutions when this derivative is actually equal to 0, which is the equilibrium state. Okay? So what we have over here is that minus H plus 2Bm plus 4Cm to the third equals 0. Okay? Now remember that B equals to some constant B multiplied by T, which is our reduced temperature. Okay? So what we have over here, in the vicinity of the reduced temperature, we have minus H plus 2BTm plus 4Cm to the third, all of this equals 0, exactly at T equals Tc. Okay? What is small b, or what is T? It's simply 0. So we have minus H plus 4Cm to the third equals 0. Okay? what we obtain? We obtain that m to the third equals to, this is bad already, m to the third equals h divided by 4c, or m is proportional to h to the power 1 over 3. Okay? So if we'll go to this behavior that we expect, we know that for delta mean field is exactly 3. Okay? And again, for many systems, we see exactly the same delta. There are different systems with different deltas, but usually we do not call that they are absolute, but we also can see different systems with exactly the same delta. What it means again for us, that there are different classes of systems, and although this general behavior of those systems is very, very different, near the critical point, the behavior becomes almost identical. Okay? How identical? For us, identical is a presence of the same critical exponent. Okay? Let's go to the third example, this gamma over here. Okay? How this guy is computed. Okay, so what we know from this guy, we can go again to this equation over here. Okay? Or this equation that we have here, right? So what we have minus h plus 2bm plus 4c m to the third equals 0. Okay? So m equals to h 1 over 2b minus 4c m to the third, right? We obtained this from this equation that was obtained previously by taking the derivative of the free energy with respect to m. Okay, so let's take a derivative with respect to h, okay, of those two guys, d to dh of the left hand side equals to d to dh of the right hand side. Okay, d to dh of m is this, this is our susceptibility he. Okay, so we have this on the left hand side. Further, we have 1 over 2b multiplied by 1 minus 4c 3m squared multiplied by, again, d xi, or I'm sorry, xi. Okay? 1 over 2 what? Should be outside of the parenthesis. Okay, so this is this guy, right? Okay. Okay, so what is we are doing next? So we having xi 1 plus 1 over 2b multiplied by 4c 3m to the second power. Okay, and all of this equals to 1 over 2b. Okay, so xi is 1 over 2b multiplied by 1 over 1 plus 4 or 12c n to the second power divided by 2b, so it's 6, and we have b over here. Okay. It looks okay, right? I haven't made any crucial mistakes. Seems fine. 2b or not 2b. Okay, now we're looking on what happens when t goes to tc. Okay, what happens in this regime? So we know that b is proportional to b multiplied by t. Okay, we know that m is proportional to t or minus t to the power 1/2. Okay, so we look on this term over here, and we have 6 and c is a constant, okay, in the vicinity of the temperature of the critical temperature stays constant. M squared is proportional to t to the power 1 or minus t, doesn't really matter. B is proportional also to t, so this term is completely independent of the temperature. Okay? The only contribution to the temperature comes from what guy? From this guy. Okay? So we observe that the susceptibility is what it is exactly, is proportional to the reduced temperature to the power -1. Okay? So from the exact description of the critical exponent, we have that our gamma of mean field equals to -1. Now this is interesting because what it actually means, +1, yep, +1. What it actually means, so here is our temperature, here we plot our susceptibility, okay? So the susceptibility near critical point, okay, there is some constant behavior or non-critical behavior for high enough temperatures. What is it exactly? What is it exactly? It's rising somehow and it becomes high enough or low enough. Something is going on over here. Now, when we approach the critical temperature from below, what we observe? Okay, what do we observe? We observe that this guy is actually explodes. Okay. Where is this coming from? This explosion of the susceptibility. So think about it, what it means, the critical transition. In the critical transition, the system has already some sort of internal magnetization. Okay? So there is an order present exactly at the critical point. Okay? So I almost do not have to apply any external field in order to make the system jump from zero magnetization or small magnetization to an extremely higher magnetization. Okay? This is why the susceptibility, okay, has this non-analytic point exactly at the critical temperature. Additional point to discuss about those critical exponents, the susceptibility is related to something which is called a correlation length. Okay? What is a correlation length? So if we look on our Ising model, right? If we look on our Ising model, so we had those particles over here. Okay. And usually we assume that, well, we can have a spin over here and a spin in some other direction, and when the temperature is extremely high, there is absolutely no influence that is coming from this particle, let's assume it particle number I, and particle number J. They are absolutely different. They don't care about each other. Okay? What is termed, they are uncorrelated. Okay? When we lower our temperature, what starts to happen is that the behavior of particle I starts to affect, those are the clusters that I tried to plot to you on our last lecture, that are starting to form clusters of particles in the vicinity of our particle I that behave in a very similar fashion as this particle. They all start to behave in a very correlated manner. When one of them is up, everybody are up. When one of them is down, everybody are down. Okay? Now, the size of this cluster, okay, usually described by some length, which is zeta over here. Okay. What starts to happen when we are approaching the critical temperature? What I already told you, the size of this cluster, they start to grow, basically meaning that this cluster length, zeta, is becoming larger and larger. At some point, this particle J that was distant enough from particle I, and they were uncoupled, their behavior was absolutely unrelated to each other, okay? This particle is also absorbed into the cluster, that is described by particle I, okay? And suddenly now, those two particles start to behave in a correlated manner. Okay? The size of this cluster, zeta, is describing the correlation length. Okay? The correlation length between two particles describes how are they behaving. If they're really close to each other, okay, and the correlation length is small, okay, they will start to behave similarly. If they're distant one from each other and the correlation length is small, they don't care about each other, so they basically are behaving in completely different manner. When one is pointing up, you cannot tell what is the direction of the other one. It can be up or down. They are uncorrelated. This correlation length basically describes who are the neighbors of our particle that behaves exactly in the same manner. Okay? Now, there is a relation between this correlation length, okay, and the susceptibility. What is the relation? Well, first of all, we can show it mathematically, but we'll do it in a hand waving fashion. So what actually happens? When I apply external field, okay, all the particles are feeling exactly the same field. Now, what starts to happen, instead of single particles that are starting to switch their direction, okay, right? What starts to happen is that exactly at the critical temperature, okay, instead of single particles switching directions, there are clusters, whole clusters of particles that are momentarily switching from being down to up. Okay? Exactly at the critical point, you see this correlation length, we say that it actually diverges. It includes the whole size of the system. So what starts to happen? The particles, there are clusters inside the system. Okay? I apply external field. Due to small application of external field, the whole system tries to flip its direction or change its magnetization according to the applied external field. This is why the susceptibility diverges. Okay? It's not that I applied small external field and some of the particles are jumped from being down to being up. Okay? What happens over here is that I have the whole cluster, because they are correlated, they're sitting exactly in the same cluster. Okay? The whole cluster is changing its direction. So this is why this guy diverges. Instead of, usually I apply small field, some small portion of the system changes its behavior. When the whole system behaves exactly as one particle, when this particle or any other particles in this cluster changes its direction, the whole system jumps, and this is why I have a huge susceptibility. I apply small field, the whole system changes its direction, and this basically means that the correlation length inside the system, how distant the particles have to be, or still, let me rephrase it, what is the distance between two particles, or the maximal distance between two particles, but they such that they are still correlated and behave in the similar fashion. Okay, this distance, which is we term a correlation length, is simply diverges. This is why we see a divergence in the susceptibility. So I told you this story. Those are very nice critical exponents. The next step, people started to realize, well, they measured huge number of them. They've been able to solve the mean field approximation exactly in the same fashion as we did here. There were very small number of exact models, like the Ising model, that we were actually capable of solving. All right? As I told you, the Ising model can be solved exactly in 1D, okay, or in 2D without application of external field. It was really hard to solve anything realistic with interaction present. Okay? Because at the point when particles are correlated, it is really, really hard to compute this partition function. In the 60s and the beginning of the 70s, people started to think about those ideas in slightly different manner. Okay? Instead of saying, let's solve everything together, okay? Let's solve exactly, like the Ising model. We can write a partition function, and we can try to uncouple those different sums. Remember, what's the problem in the Ising model? The problem is that the energy the energy of the Ising model was a sum minus of SI mu H minus J over 2, a sum of I, a sum of J, SI, Sj, and this is when the interaction is extremely short. Okay. The problem was that we have a double sum over here, and we cannot simply resum all of this to new coordinates that won't have double summation, but will have only single summation, because only when we have single summation we can say we have factorization, and we know how to solve or to write partition function for factorizable systems. Okay? We know how to do it for Ising model only in 2D, and only when those interactions are extremely short-ranged. Okay? And most of the people were extremely stuck, theorists. From experimental point of view, people measured those critical exponents, different critical exponents in different systems, and there was already a zoo of them, okay, because I termed only 3, but there are several different, many critical exponents, and people started to understand that there are classes of systems, but they still do not really understand what those classes means. And at the end of the 60s, the beginning of the 70s, started to develop quite a new and fascinating approach, which was termed the renormalization group. Renormalization group. What's the idea of renormalization? The idea of renormalization is as follows. So what we can solve? We can solve a system, okay, without any interactions. As usual, we can solve only systems that are gaseous, right? Free particles. Okay, so I have told you all those stories about correlations lengths and clusters, etc., etc., etc. So let's assume that we are approaching the critical temperature. Now, if the temperature is extremely high, okay, what we can do, we can look on different particles and say they are completely non-interacting, right? When we approach to the critical temperature, what we start to see that the particles start to interact, okay? We can then renormalize everything. So what we know that they are starting to appear clusters of particles, okay? Instead of looking on this guy, so those 3 guys behave in a similar fashion, and those 3 guys behave in a similar fashion, and those 3 guys behave in a similar fashion, and also those 3 guys also behave in a similar fashion. Now what we can do, instead of looking on one single particle, we can say, Well, let's renormalize everything. What it means, we can color 3 of those guys and say those 3 guys are one single particle. Those 3 guys are also one single particle. Those 3 guys are also one single particle. And also those 3 guys are also one single particle. Okay? What we do next, we do this exactly the same. We lower the temperature a little bit further. Then we start to see correlations between this new particle and the other new particles. Then we create bigger clusters. Right? Doing this repeatedly, we can construct a theory. This is the renormalization group theory that describes everything as some sort of new non-interacting particles, but those new non-interacting particles are becoming bigger and bigger and bigger. Okay? And the extremely neat trick that was due to Leo Kadanoff, he passed away 2 years ago, was to actually take the limit when the sizes of those new particles becoming extremely large, and then we can start to understand what actually happens near the critical temperature. Okay? So this is a neat mathematical theory that describes of how one can treat growing particles when we constantly renormalize their size. There are extremely interesting, really extremely interesting connections between the theory of statistical mechanics near equilibrium and a very simple question in probability theory. Okay? Because what I'm actually describing to you, think about this particle. This particle, this one original particle, I can say that this is a random variable. Why? It can have 2 positions, +1 and -1. All of the other guys are also random variables. So I can say when I sum up over all different spins, okay, I can say this is my x. It is a sum of I over Si. Okay? I goes from 1 to n. Si's are random variables. N is very big. Okay? What is the statistics of x when n is large enough? And all the s's are independent and bounded. Okay? You know this. You learned this in first year. Central limit theorem. Okay? Gaussian central limit theorem. We can always perform this summation when the particles are when the random variables are independent, okay, not correlated. We can always find the statistics of x. It will behave in some Gaussian fashion, and this is why we can always obtain the partition function for independent particles. Okay? What happens near phase transitions? Okay? So what we start to see that our different random variables start to behave in a correlated manner. Okay? And the correlation length between 2 particles becoming larger and larger and larger. Okay? So at some point we have to go from this very simple theory that is described by Gaussian statistics, okay, into the same question when we say this is no COT, no central limit theorem, where we have a sum over I goes from 1 to n, when the different SIs are now correlated and dependent of each other. Okay? When you studied statistics in your first year, okay, you simply proved what is the statistics, what is the behavior of a sum of a random number of variables. It's easy to prove, it's easy to see that it's Gaussian, etc., etc. The moment there are correlations, okay, the moment there are correlations, everything breaks. Okay? Absolutely everything breaks. You do not have some general theories, mathematical theories about what is the limit distribution of such a sum. Okay? Now, what exactly is being done in the vicinity of the critical point is, on the creation of different classes, is basically a statement that we don't really know how a sum of correlated random variables behaves. Even now, we don't know if there is only one single behavior, like a Gaussian over here, or there are classes, and what is the distinction between different classes, okay? And this question is still open in statistical mechanics and also in probability theory and mathematics. So it's time to finish. We won't study any new material. I hope you all will succeed in the final exam, and thank you for your time.